Norton's theorem is similar to Thevenin's theorem, with the difference that Norton's theorem is dealing with current sources. The Norton's theorem states that a linear, two-terminal circuit can be replaced by an equivalent circuit consisting of a current source, I, subscript Norton, in parallel with a resistor, R, subscript Norton. Which means that any circuit can be replaced by an equivalent circuit consisting of a current source and a parallel resistor where R, Norton, is the parallel resistance at the terminals, and I, subscript Norton, is the current source. We are going to use this same example that we started out with, looking at the Thevenin equivalent. But this time, we're going to calculate the Norton equivalent for this circuit. Again, we're choosing R2, the 2 ohm load resistor, as our load. So we're going to now replace everything else in the circuit with the Norton equivalent, which is a current source in parallel with its internal resistance. Remember that a current source is a component whose job it is to provide a constant amount of current, outputting as much or as little energy necessary to maintain a constant current flow. That means the voltage will rise and lower, but the current must remain constant. As with Thevenin's theorem, everything in the original circuit except the load resistance will be reduced to an equivalent circuit that is simpler to analyze. Also similar to Thevenin's theorem are the steps used in Norton's theorem to calculate the Norton source current, I, subscript Norton, and the Norton resistance, R, subscript Norton. As before, the first step is to identify the load resistance and remove it from the original circuit. Then, to find the Norton current for the current source of the Norton equivalent circuit, place a direct wire or a short connection between the load points and determine the resultant current. Note that this step is exactly opposite of the respective step in Thevenin's theorem, where we replace the load resistor with an open circuit. With zero voltage drop between the load resistor connection points, the current through R1 is strictly a function of B1's voltage and R1's resistance. 7 amps. And I is equal to V over R. And likewise, the current through R3 is now strictly a function of B2's voltage and R3's resistance. 7 amps. And we can again use Ohm's law, I equals V over R. The total current through the short between the load connection points is the sum of these two currents, 7 amps plus 7 amps, which is equal to 14 amps. Therefore, the Norton source current I, subscription Norton, in our equivalent circuit is 14 amps. To calculate the Norton resistance, we do exactly the same thing as we did for calculating the Thevenin resistance. Take the original circuit with the load resistor still removed, remove the power sources in the same style as we did with the superposition theorem. The voltage sources are replaced with shorts. Then calculate the total resistance, which is R1 and R3 in parallel. The Norton resistance in this case is 0.8 ohms.
Stay tuned to this site, as I'll be diving into more information from my electrical courses. In the meantime, take advantage of the availability of my 50-page electrical power crib sheets by simply filling out the information when you go to this website, https://bit.ly/47 uppercase Y, uppercase B, 3 lowercase v, and lowercase h. You can also directly access my StanStore courses at this website, https://lowercase stan.store/uppercase G, uppercase V, uppercase B.